Part 1. Prepare a drink, such as a glass of water, if you can. Then, please find a quiet place to sit and to listen to this audio. Once seated, close your eyes. Focus your attention on your breath. When you're ready, inhale slowly. Let the air fill your lungs. And then exhale slowly. Let the air escape from your lungs. Inhale again, and then exhale again. Notice how your stomach rises as you inhale and falls as you exhale. Rises as you inhale and falls as you exhale. If your mind wanders, don't be concerned. Just gradually shift your attention back to my voice. Part 2. Now, if possible, lift your glass, bottle or cup. Observe how this container feels in your hands. Perhaps the glass feels cold or hard. Perhaps the bottle feels smooth or jagged. Now, if possible, sip the drink. Observe how the liquid feels while pouring into your mouth. Feel the sensations in your lips, on your tongue, on your palate, and in your throat. Perhaps the fluid seems soft and light. So why do we need to drink water? That is, why is dehydration, inadequate water, so damaging? Actually, we need water to achieve two purposes. First, we need to ensure our blood contains enough fluid. Imagine the problems you'd experience if your blood contained minimal fluid. That is, visualize your blood vessels, a network of pipes throughout your body, is almost empty. Consequently, the blood could only limply press against the walls. In other words, your blood pressure would be limited. Therefore, the heart could not pump the blood to the brain effectively. Each pump of the heart pushes the blood just lifelessly along the vessels. The blood does not flow to the brain adequately. Not enough oxygen, glucose or other nutrients enter the brain. Second, we need to ensure the concentration of molecules outside our cells is the same as the concentration of molecules inside cells. So to illustrate, suppose you could watch the fluid outside your cells, such as the fluids that surround your neurons or the blood in your vessels. And imagine you could actually see the number of molecules in this fluid and the number of molecules in your cells, such as the neurons. Perhaps the molecules resemble small M&Ms or tiny ribbons or some other shape. And these molecules include salt and many other chemicals. Try to watch these shapes float both inside and outside your neurons or other cells. So what problems would unfold if you had not consumed enough fluid? You can imagine the volume of fluid around your cells subsides, while the number of molecules, the number of shapes in your fluid remains the same. So therefore the molecules become more concentrated, more crowded outside the cells than inside the cells. And because of a process called osmosis, this concentration of molecules outside the cells attracts fluid from inside the cells. Fluid thus flows from the cells to the surrounding fluid. Perhaps you can hear the fluid gush from the cells to the surroundings, like the sound of flowing water. Consequently, the cells contain inadequate fluid and water. Chemical reactions within the cells are impeded, and the cells don't function properly. Don't worry if your understanding of this topic is still hazy. You don't need to devote any effort into this exercise. You merely need to follow the instructions. This meditation shows how the body responds to this second problem, a high concentration of molecules outside the cells called osmotic thirst. So how does the brain detect this concentration of molecules such as salt? Well, to answer this question, visualize the blood in your vessels migrating around your body. Then focus your attention on the blood vessels in your brain. Direct your attention to the inner lining of these blood vessels. And the inner lining of these blood vessels comprises many small oval cells called endothelial cells. As you visualize this inner lining of blood vessels, repeat the term endothelial cells. Endothelial cells. Endothelial cells. Don't worry if you can't remember the name of these endothelial cells. Simply maintain the image of blood vessels in the brain like small pipes lined with these small oval cells. Usually in the brain, these oval cells are crammed tightly together. Few molecules are able to squeeze between these cells and leave the blood vessels. So few molecules shift from the blood to the brain cells. Perhaps you can imagine or hear a loud clunk as molecules resembling M&Ms or small ribbons crash against the small oval cells that line the blood vessels in the brain. However, in some regions of the brain, these endothelial cells are not as tightly packed together, and one of these regions is called the third ventricle. The third ventricle is located just above the midbrain and brainstem. And this ventricle is really just a sac of fluid in the middle of your brain. And molecules often shift from the blood vessels in this region to brain cells that surround this third ventricle or sac of fluid. Now, two strips of cells near this sac detect the concentration of certain molecules, in particular salt, in the fluid. One strip or region is towards the front of this ventricle and is called the OVLT, an acronym that represents Organum Vasculosum Laminae Terminalis. But most individuals, for obvious reasons, call this region the OVLT. If possible, try to visualize this strip of cells toward the front of the third ventricle in the middle of your brain. And while you maintain this image, repeat the acronym OVLT. OVLT, OVLT. The other strip or region is above the ventricle and called the subfornical region. And if possible, try to visualize this strip of cells at the top of this third ventricle in the middle of your brain. And while you maintain this image, repeat the phrase subfornical region, subfornical region, subfornical region. So what events unfold whenever people don't drink enough and the concentration of molecules, especially salt, in the fluid outside cells increases? Well, receptors in the OVLT, subfornical region, and even the stomach are activated. That is, these receptors send action potentials like sparks of energy whenever the concentration of salt in the fluid outside cells escalates. Don't worry if you can't remember the names of these regions. Just be aware that high levels of salt in the blood activate cells in both the brain and stomach to generate action potentials or sparks of energy. Part 5. In particular, these receptors send these sparks of energy to various parts of the hypothalamus, a small but vital region of the brain. Now, to visualize the hypothalamus, imagine you could drill horizontally between someone's eyebrows into their brain for about 4 centimeters. And you then notice a structure behind this point that resembles about 15 tiny jelly beans of different sizes, each lying at a different angle, jammed together. And each of these jelly beans is a distinct cluster of neurons called a nucleus. And each jelly bean has been assigned a different name, such as lateral preoptic nucleus or area, the supraoptic nucleus, and the paraventricular nucleus. To illustrate the role of this hypothalamus, focus your attention again on the receptors in the OVLT, subfornical region, and stomach that send action potentials like sparks of energy to this hypothalamus whenever the concentration of salt in the fluid outside cells escalates. In particular, these receptors send these sparks of energy to a part of the hypothalamus, or jelly bean, called the lateral preoptic area, or lateral preoptic nucleus. And this region somehow motivates people to drink. That is, when this region is activated, people are more likely to feel thirsty. They are therefore more inclined to drink. You do not at this moment need to remember the term lateral preoptic area. You merely need to know that receptors that detect elevated concentration of salt in fluid send messages to regions that encourage drinking. In addition, these receptors in the OVLT subfornical region stomach also send action potentials to two other parts of the hypothalamus, the supraoptic nucleus and the paraventricular nucleus. And in response, these two regions produce a hormone called vasopressin, a hormone that's also called antidiuretic hormone. Perhaps you can imagine the hypothalamus, embedded within the cortex, releasing some chemical like curly ribbons into the bloodstream. You can then imagine this chemical float around the body, from the head to the neck, chest, organs, arms and legs. And while you maintain this image, repeat the terms vasopressin or antidiuretic hormone, vasopressin or antidiuretic hormone, vasopressin or antidiuretic hormone. So what is the effect of this hormone? Why does the hypothalamus produce this hormone whenever people don't drink enough fluids? Well, this hormone generates two main benefits. First, while migrating around the body, this hormone constricts blood vessels. Perhaps you can imagine vasopressin attached to the blood vessels, and then you can watch the blood vessels tighten as a consequence. And so the increase in blood pressure helps the heart pump blood to the brain. But this increase in blood pressure doesn't diminish the concentration of molecules in the fluid outside cells, the topic of this meditation. But second, vasopressin also helps the kidney retain fluid. That is, usually the kidneys extract water and waste from the blood and send this fluid down tubes called ureters to the bladder. But vasopressin helps tubes in the kidney reabsorb some of this water, so the water is channeled back into the blood rather than excreted as urine. The water is thus conserved. Don't worry if you can't remember the details. Just accept that high levels of salt in the blood, because of dehydration, activate many regions of the brain and stomach. And these regions in turn activate parts of the hypothalamus, an area that resembles about 15 tiny jelly beans, about 4 centimetres behind the eyebrow. The hypothalamus then incites the urge to drink, but also produces vasopressin, or hormone that retains water and offsets the consequences of dehydration.